Okay, it's on. So we'll be talking about clustering today. As usual, right, this particular XKCD comic is not quite about clustering, but I find it interesting nonetheless because a visual representation of similar data points gives us a perspective of how bad we are to the planet. And from this chart, there's also a lot of like simple actions that people can take in order to make it less bad, and hopefully much less bad for our next generations and so on, which is to eat less meat, especially I guess cow's meat are bad. So there's that. So what we're actually going to talk about today is mixture models and expectation maximization. With this, I guess you've been warned, and like on the course schedule in Piazza, and we said that we assume that you know what the k-means algorithm does. And then we assume that you have seen the update equations of Gaussian mixture models at least once. So we'll start with a recap of that, and then quickly go to essentially two different views of EM, two other views of EM. Other than the algorithm, we first ask, what is the M-step maximizing? And then we ask, what is the entire EM algorithm maximizing? I think we know the answer because we've been just maximizing likelihoods in most of this class. So we expect you to really maximize likelihood, but why? Yeah, and then we can talk a bit more generally about clustering and when things don't work and how to make things work better. So in terms of the sheer amount of visual content and slides, I think this is one of the lighter courses. But in terms of conceptual content, I still think there is basically a few steps that we shall take together. So first of all, let's do a quick warm-up. What is clustering and what are the goals? For those of you who have taken IML or seen it in other courses, it might have been a while, right? So the goal of clustering is to find inherent groups in data. For example, this picture in the book, I believe it's the old Facebook data set where it's the eruption time and time interval between eruptions of a famous geyser in Yellowstone National Park in the US. So you can visually see, while the green dots are data, there might be two groups. So assuming we know how many groups we want to find beforehand, k-means and Gaussian mixture models are both algorithms for us to find these groups. For k-means, for example, we start with some random centers or random data points as centers, maybe better. And then we hope to basically have the algorithm to converge into the bigger group on the upper right-hand side and the slightly smaller group on the lower left-hand side. Right. So k-means works by assigning each like introduce a prototype for each cluster, and then we want to find a set of prototypes so that we assign each data point to this cluster, and it's kind of descriptive to the whole data set. So I just wanted to include a side quip or a bit of a modern perspective on the goals of clustering. What I'm about to say comes from this paper, Clustering, Is It a Science or Art? It's written in 2012 by a group of researchers who are still active. All of them are still active in machine learning. Ulrike von Luxemburg in Germany, Robert Williamson who have worked at ANU for a long time and now is also in Germany, and Isabel Graham. She is currently professor at Paris, and she's been living in the Bay Area or near Berkeley for a long time, right? So the paper, part of the paper says, well, the goals of clustering is actually not precisely defined. It entirely depends on the application domain, the task, and what you want to do with it. Like, do with the clustering result, how you want to interpret and use it. Moreover, the criteria that we use for clustering is also very much domain, task, and use dependent. As an anecdote, they say that, well, people say that in the Chinese encyclopedia called the Heavenly Emporium of Benevolent Knowledge, in its distant pages from ancient China, apparently the animals are divided into a large number of groups. Like, for example, we can read this. So it's divided into, those that belong to the emperor, inbound ones, those that are trained, suckling pigs, mermaids. Anyway, you get the idea. I don't know if this is true, despite, like, I originally come from China, but you can see that some of the conceptual groupings it might at least appear weird to people who are not clued into the context, right? So, yeah, Heavenly Emporium of Distant Benevolent Knowledge might be actually written to serve the emperor. Therefore, like, maybe there's a reason for the first category, but it leaves us to muse on the rest. Anyway, so the side note part, here is an overview of k-means and Gaussian mixtures, which I assume you already know. So the expectation step in k-means is to assign data points to the closest cluster, denoted by these what's called the responsibility variables in the book. They are either 0 or 1. 0 meaning data point n is not in cluster K, 1 meaning data point n is in cluster K. And then followed by maximization step, basically average all the data points in a cluster K to come up with its means. So on the all faithful data set, it looks like this, right? So we get a red grouping and blue grouping that looks kind of reasonable. So in contrast, in Gaussian mixture models, the E step computes, again, the responsibility variables. But in this case, these are probabilities. So this lives in 0, the reals between 0 and 1. And then the M steps updates the parameters, means, covariance, and prior probability for each mixture component using the responsibility variable and the data points. Okay, and on the same all faithful data set, it finds groupings like this. So not only does it assign almost the same set of red points to the red cluster and blue points to the blue cluster, it also, for example, finds the mean and also finds the covariance matrix, which has additional information on in which direction the cluster spreads, right? All right, so you mean, right, you can ask whether k-means and, right. So one salient difference is the hard versus soft assignment, right? This, you can ask whether that's the only difference. We will have a slide about that later on. But for now, let's look at one view to connect the two conceptually. So for k-means, we have the hard assignment variable R sub nk. For GMM, we have soft assignments, basically the cluster posterior probability, gamma of znk. So if we take a Gaussian mixture model assume that the covariant matrices of all components are spherical with variance epsilon, right? And all the dimensions are uncorrelated, so it's a identity matrix scaled by epsilon. The probability of gate data given the cluster is then written as a Gaussian probability distribution function. Because the covariance is identity scale identity, so in here we just get the L2 norm rather than the covariance matrix inverse in the middle. And here is the corresponding calculation for the responsibility variables. So basically, the probability of the data point under the current cluster K normalized by the conditional probability of the current data point under all components, right? So if we take the limit of epsilon shrinking to 0, then because there's exponentiation, the largest component among these sums will dominate. Right? So if epsilon shrinks to 0, then this term approaches 0 from above. Then the term inside approaches infinity, but the term with the smallest distance will dominate. So this is essentially softmax, right? But square distance, softmax with square distance. For those of you who know softmax, this should be straightforward. Otherwise, yeah, it's a work on the reason with your calculus and the limits. So basically, if someone shrinks to 0, these soft assignment variables becomes the hard assignment variables. Right. So that is a useful observation for connecting these two. We'll come back to the whole suite of it later on. So then let's talk about like the first of the two key questions that we are going to ask in this lecture. You may say, right, EM is an iterative algorithm, right? We first do the E step and then we do the M step. So what is being maximized here, right? We first ask what is being maximized in the M step. And later, well, in the next section, we will ask whether this overall procedure maximizes the likelihood. In the book, when it's first derived, right? So I think the book has very good reasons of having to talk about this 3 times. In the first time that it was talked about, right? So the data likelihood was written out in version 9.14 and also 9.28. It is, for example, the prior times the Gaussian probability for each data point, for each component, summed over all the components. And then the log likelihood is basically taking the product across different data points outside the log. So it's sum over logs, it's a log of sums, right? So this makes it a bit nasty to work with because this sum, we cannot take it out of the log, and hence the familiar trick of like taking apart the phi and the exponential terms don't work anymore. But let's say we take the partial derivative of this anyway. So this was in the EM section. Then the partial derivative look like this. So because there's a log, therefore, due to chain rule, there is the summation term that comes to the denominator. And then applying chain rule, we first copy that term and then, or actually, and then differentiate with respect to, okay, this is, then we essentially get the linear term scaled by the covariance matrices. And the book then said, look, right, the front term looks a bit long, but it's essentially the responsibility variables that we are calculating. So, and then we just plug in the responsibility variables we just calculated, and we get the M step, right? So this is how EM was presented. But in fact, this is cheating a little because we're taking partial derivative with respect to mu of k, but mu of k is also being used in the partial derivative, in the responsibility variables, right? So what is happening then? So strictly speaking, this is not a direct maximization of this original likelihood log likelihood function. We can also see this in hindsight, right? So if this were a maximizer for the entire likelihood function, we would not need to do the iterative procedure anymore. Like what we did before, we can just maximize it, right? Solve it analytically. Okay, so we were just poking holes in the vanilla EM and asking questions. Now let's try and answer it. So first, let me explain this picture. So in the book, this is presented as chapter 9, right after the graphical model chapter. But right now we're learning it before the graphical model. We actually talk about graphical models. But these are like the simplest graphical models that we can explain without all the context. And it will be good. I think it's actually conceptually good for us to see graphical model more than once. So here's consider this a warm-up, right? So each random variable is a circle. And then the arrows of the circle or between the random variables determine how basically which way the conditional probabilities go, right? So this arrow represents we are conditioning X on Z. That's how we generate data rather than the other way around. Because the book is being Bayesian, and there are good reasons, so we write all like the collection of parameters as theta, and then Z depend on theta because of the prior probabilities pi. Z are the binary cluster assignments, right? And then X depend on theta given Z. So in particular, so this reflects right X depending on Z and theta, wherein here theta means both mu and sigma once Z is given, right? And this thing, this black square is called the plate notation. It just means there are n copies of this diagram being like inside being generated, representing n data points. X1 all the way to Xn, right? Yeah, interesting. I think the plate notation was also invented somewhere around here by a researcher called Ray Buntine, who used to work here, and recently, for the past few years, worked at Monash and recently moved to Vietnam. And his expertise are like topic models for text, which uses a lot of plate notations and Bayesian inference in general. All right. So 9.29 was basically 9.28 rewritten with the notation of Z, X, and theta. So it's the likelihood function of in here one data point being log of the sum over different components, different values of Z. That's what it says. So the claim on this page, as we will try and convince ourselves in a little bit, is yes, we compute the posterior probability of P of Z given X. So these are the responsibility variables. Make a smaller k. Right, so with Z nk is either 0 or 1. And only one of these z's should be 1 across all k components. So this is that. And the E step is essentially taking expectation of what's called the complete data likelihood, log likelihood. So Z is unobserved. We only observe data point X. If we assume Z is observed, so this Z is also called latent. So if we now assume Z and K is observed, then we call this term essentially complete data likelihood. Right. And what does this mean, right? And the expectation is taken with respect to Z. In particular, it's taken with respect to the conditional probability of Z given X and theta. So written fully, basically the mathematical expression of the line above is the object that we're taking likelihood on is this complete data probability P of X comma Z given theta. We're taking expectation over the likelihood, therefore there's a log in front. And the distribution, right, we're taking this expectation with respect to these gamma variables, essentially. Therefore, there's a summation over Z inside. So as we can see, the result of this function will have three kind of things inside, right? So what we did in the M step was to actually update the parameters using the responsibility probabilities computed using the old parameters, right? So now we separate essentially theta new and theta old, and it will also have X in it because we marginalized or summed over Z, but we haven't summed over X. Stated a bit more formally is if we call this complete data log likelihood term curly Q, we're computing argmax of Q, which is function of both the old and new parameters. That will give us the new parameters, and this expectation is being maximized in the process. That might be a mouthful. This slide is a mouthful, and it's spoiling the ending for you guys. But here is how this is done, right? So let's first stare at the same graphical model now, just with the Z shaded, meaning that we also observe Z right now, rather than it being unobserved. We operate in this scheme, right? So if we have complete data likelihood, and we claim we want to basically show 9.31, and 9.28 is our data likelihood function over data set. Now, if we just assume Z being observed, the complete data likelihood in the non-logged term will be like this. Basically, for each for Z of nk, we again use the exponentiating trick. When Z of nk is 1, that term is active. When Z of n sub k, Z sub nk is 0, the term is inactive, right? So like 1 in these k terms is is active. So I will add only one of these k terms active. And then this probability is sort of also multiplied through the n data points star I and d. Right. So we like product signs when we're taking log. So that's what's happening. I just apply the log function to this, and I end up with two summation signs. And I also apply the log inside this. So the exponent z of nk comes out as a multiplier. And then we can also separate out pi and the log of the Gaussian probability. So great, we are in our familiar realm because we've seen MLE on Gaussian for so many times. Let's also just write out the responsibility variables. So this is basically gamma. It's actually, well, we might want to call it big gamma because it's, again, over all components and over all data points. So you may say, wait, what am I staring at here? So this expression, this whole part in 9.38 is actually exactly the same as 9.35. So you're saying the posterior of cluster assignment is sort of a same expression with data likelihood, complete data likelihood. So yes and no, right? So it does look the same, but the key difference here is the proportional side. Which is what we were saying. Basically, the full probability needs to be normalized against the sum overall cluster assignments. It's better written this way because right now this writes it over all data points as well. And each data point has a different cluster assignment. If we start writing out the normalizing term, it will be quite impossible. Or it will, fill the page without adding much, right? So these are, I guess, not magic stuff that we've already seen. Now, we just defined this Q term on last page as the expectation of the complete data likelihood, which was this term, or actually this term that comes here, this term comes here, over Z. And the expectation here is done over this conditional or cluster posterior probability. Okay, with these two components, we can see that we can just plug in the responsibility probabilities times the likelihood for each of the Gaussian components. Okay, so this basically says the Q term writes out to be this, with theta old being in the first part and theta new being in the second part. So, right, last page is a mouthful. Hopefully we decomposed it a little and it makes sense now. By the way, I wanted to ask you guys if anyone can see the chat or channel content. I could not. So.
Yeah, there are messages.
Let me see. Oh, right, there are a few messages. So that's strange. So my computer can get into the meeting, but hasn't. Right. Okay, I'm staring at the three messages right now. The sum most possibility doesn't equal to 1. Yeah, I'm not sure which one you're referring to. maybe I'll answer this one last, and I ask you to clarify. So what's the purpose of using a latent variable z here? It is because in clustering, we don't know the cluster assignment. Like what we want to recover from a data set is actually the cluster assignment, right? So the whole procedure tries to basically come up with a plausible set of assignments. And calling a latent variable is basically a mathematical tool that allows us to reason about it without having it observed in the first place. That's just a high level summary. If not, we can elaborate. Like if that doesn't help, we can elaborate at the end. And okay, all the likelihoods until now are all in Gaussians. Great question. So in this session, we're going to see Bernoulli. In your homework, you're going to work on exponential family. And you're also going to work on Bayesian linear regression in question 3. Gaussians are easy to manipulate, and it is so there are 2 reasons for using Gaussians. A, it's easy to manipulate. It makes perfect pedagogical sense. B, Gaussians appear like they describe lots of real-world data really well because of, let's say, central limit theorem, like law of large numbers, and these limit theorems that you would have already seen earlier, because real-world data is sort of comes about from the independent force from many different real-world factors. I hope that helps. So once you understand Gaussians, you can essentially use it to bootstrap into almost any distribution, even distributions that we can't analytically sort of do the M step. We can use sampling. In fact, in last year's exam question, as you will see, there is a question about doing this for exponential distributions, which is a simple case. Right, so there's a new question. Why do we update sigma with new mu? Good question. So Fei Yang asked that. Let me go back to the slides and show you that. The short answer is when we do MLE, maximum likelihood estimate for one Gaussian, we update the sigma with the new mu as well. So in essence, what do we? Okay, so the expectation step essentially updates. So if I can just interpret these update steps, right? So the expectation step updates these responsibility variables, right? And then the maximization step update the rest. Update by the collection of mu k's and sigma k's for k equals to, yeah, their range. I hope that makes sense. So if we take an optimization view, which is slightly outside of the scope here, but for those of you know, right, if we're basically optimizing a high dimensional function that has many local minimums and so on, here assuming we're minimizing, this is essentially a coordinate descent algorithm where the coordinates are the gammas and the parameters, and in one batch we update all the gammas, in another batch we update all the parameters, and I hope that helps. And if we can do it in 2 batches, but I think it's easier to do that rather than doing it, for example, in 3 batches. It's a bit hand wavy. I hope that helps. Okay. So feel free to interrupt me and remind me, like, when there's questions, I remember to pause. So this is a summary of the more general EM algorithm that we are talking about. And this general EM recipe applies to more than Gaussians. As you will get to convince yourself in question, I believe it's 2.1. Well, basically the first part of question 2 in your homework on the exponential family. Okay, so we observe some data X, and we assume what's called a latent variable or cluster membership Z. We can write out its joint distribution P of X comma Z. And the goal is to maximize the likelihood function P of X given theta. So we initialize the parameter somehow, and then in each step, we evaluate the responsibility variables, P of Z, posterior of Z given X. And then in M step, we essentially maximize this curly Q function, which in this case treats the X as data or fixed input, and then it maximizes this Q function with respect to theta nu holding theta O fixed, where theta O goes into calculating these posteriors for the latent variables, and theta nu goes inside the log term. Right. You could also, this is maximum likelihood, right? So we've been taking a Bayesian view. If we have a prior on theta, we could essentially incorporate the prior into this Q term. Right, and then we keep doing this until we converge or we decide to stop, and we check for convergence of either the log likelihood, the original log likelihood, or in the parameter values. If the parameters don't change, then the corresponding posterior responsibilities also don't change. Right, if the convergence criteria is not satisfied, then update the parameters and go do this step from step 2 again. Right, I hope that makes some sense. Right, I moved this slide and I forgot to delete it. So basically we already talked about this. Yeah, so what I haven't done was to essentially take the partial derivative of this E of Z term with respect to things like mu k, pi k, and so on. I leave that for offline because I felt like we have done this enough times in the class. But if you would like us to go through it, just raise a question. That's also because I think we can talk about other things that are slightly more new. Let's talk about k-means and GMM, and then I'm going to check on the questions again. So in Gaussian mixture models, the data likelihood, like without the latent variable Z, is as follows, right? So this is essentially sum over Z. It looks like this. And in k-means, the objective function. So just bear with me, right? So we claim that this is being this data likelihood is being maximized, and we're doing MLE. I haven't showed you or convinced you of that, but we'll get there in the next part, right? So for now, let's say in GMM, we maximize the likelihood. In k-means, we minimize the distance between the data point and its corresponding centers, right? The cluster centers. And then because of these responsibility assignment variables at 0 or 1, so it's one term active. Yeah. So in GMMs, it's not exactly one term active because the Gaussian probabilities are not exactly 0, even if you are somewhere far away from it. So we've seen Gaussian enough times. And we might be able to spot that, right? So inside this Gaussian probability, there's some normalizer that we omit. And then we have x, essentially x minus mu k, xn minus mu k transpose, inverse of sigma k, x n minus mu k, no transpose, right? So there's this term. If we do log of x, we know there's a sum in front, but again, going back to when we say the epsilon, if these GMMs have isotropic and small covariance, we can actually take the log, then the log and x cancels out. Then we're back into the, and if this is like spherical covariance, then we're essentially back to somewhere. So this term above will look something like the term below. I guess we are not a stranger in the past 3 weeks to something like minimizing least square error, converting to some underlying Gaussian as the more general probabilistic interpretation. I just wanted to say that we're seeing the same thing here. I hope that makes some sense. So this particular slide hones into a little more of it. So if we compare the update equations between k-means and GMM, we can also see that, well, in k-means the mu k, well, in k-means we don't so the means, cluster means are essentially right, the means of the corresponding points in the cluster, which can be written like this. In GMMs, like it's the weighted means using the responsibility variable. So it's the soft and hard assignment, the connection between these we already talked about. And the estimates of the covariances in k-means, we don't do it. We assume it's fixed. Spherical Gaussian. In GMMs, we update it. So in k-means, the prior of each cluster do not matter. And then in terms of calculating the effective number of data points in each cluster, we either sum up the binary assignment in k-means or the real valued responsibility variables in Gaussian GMMs. So each of these expressions, well, at least the NKs and UK updates are quite similar in spirit. Hopefully, that also convinces you like the k-means and GMM loss functions or objective functions are quite similar. So when do we prefer one versus the other? One question we ask is what kind of representations do we want, right? So if the data is d-dimensional, x n is in two-dimensional reals, well, k-means have essentially k times d parameters, right? Where GMMs will have k parameters for the pi's, and then k times d for the mu's, and then essentially k times the size of the covariance matrix, which is not exactly d squared, it's symmetric, it's this, right? Yeah, I think. So if we have lots of data that we can afford to estimate that much covariance parameters, then go for it. If not, we can, for example, if D is 1,000,000, we probably do not want to estimate the full covariance matrix, but we can sometimes still estimate GMMs, for example, by assuming spherical covariances, but the size of each ball can be a bit different for each cluster, which can be a useful thing to do. All right, And then there's a whole bunch of implementation issues that could arise if you just chuck this into Python. And this is usually swept under the carpet for a class like this. For k-means, for example, the cases where when I say what if a cluster center die, basically if no point is assigned to it, what happens? In most modern implementations, the package already takes care of this for you. So one sensible thing to do is to, well, if the cluster has no points, then maybe just initialize another center, right? You could choose to just randomly initialize or initialize by splitting the biggest cluster, somehow define number of points or diameter or somehow. And also notice that, right, we could do this without problem as an estimate for the covariance. But this, the outer product of a data point or all the sum of the outer product of all data points with respect to the cluster center mean is not guaranteed to be, it's still symmetric, but it's not guaranteed to be full rank. And that can be a problem because on the last page, right, so we have seen this term, right? So this will be used in term like x minus min k, sigma k inverse x minus min k transpose here. So if sigma k is singular, then we have a problem when we plug it back into the likelihood term. It graphically, well, speaking, if let's say if we have a 3-dimensional, or let's say even 2-dimensional Gaussian, where the covariance is usually elliptical like this. In general one, it's like slanted and sort of elliptical. But if this crashes into some really elongated one that are close to a line, then we have a problem. So the way to do this is also to regularize. Like remember in linear regression, regularizer essentially adds like lambda I to the matrix that we're inverting. So in here, you could also sort of enforce that the smallest eigenvalue of this matrix does not shrink below a limit. And normalize your data, of course. If your data is, for example, one dimension of the data is a million times sort of more in magnitude than another dimension, then that's a bad idea to start with. Right. So let me check the chat for questions. Nope. Right. So you asked for non-Gaussian likelihoods. Here we go. Again, Bernoulli distribution is simple. So we assume we have a set of d binary variables, each governed by a separate distribution with mean mu I. I should say that when I read through this, it starts a little bit counterintuitive, but basically the data is live in d dimensions. So there are d zeros and ones, but the cluster assignment for these d binary variables are shared. I think this is crafted to suit the example that the book presents, but let's just bear with me, right? So this is essentially the cluster conditional likelihood. So within a cluster defined by mu, the probability of x is the binary vector is this term, right? Again, so the xi turned i's component like on and off, depending on whether it's 0 and 1. And because it's set up this way, the expectation of these Bernoullis are just mu. The covariance is diagonal matrix with mu times 1 minus mu I because the different dimensions are not correlated. Okay. And the mixture of Bernoulli distributions is this notation. So this X is a vector, say x1, xd. And then this mu is now a matrix. Okay, I'm just going to write it the same way as the X. So yeah, it's D rows and then K columns. Like will be mu11, D1. Yeah, so mu1K all the way to mu DK, right? And then there are pi, the priors. Okay, so now we have K. Clusters. The data likelihood with latent or unobserved cluster assignment is written like this. It's the same with Gaussians, right? Except we write P right now rather than the Gaussian likelihood. And then given the cluster assignment K, data likelihood is this, right? Again, it's Bernoulli. D Bernoullis multiplied together. This is then the expectation of X is simply weighted version of mu K. That's intuitive. And then as we said on the last page, the covariance matrix of each of the components is this diagonal matrix by definition. And then this bit, the covariance of X under the mixture model has a few parts, right? So the second part, like we know that the covariance is essentially E of X. Like for a scalar, roughly it's E of X squared minus E of X squared, something like that, right? So the second part corresponding to the square of the expectation itself. The first part is a weighted sum of the covariance matrix plus the outer product of the mean. It has two terms because essentially the cluster assignment for the D components are tied, as I mentioned earlier. Right, then, so because these are like the complete data likelihood, so this is basically a algebraic exercise. So the complete data likelihood is a product, right? Basically plug this into the, put the pi k in front, and then we can take the log, go through the exercise of constructing the curly Q function, which is this, and then maximizing it. Let's say that I won't try and go through this in real time. If you want, ask me a question afterwards. So the update equations turned out to be intuitive as well. So the responsibility vectors are essentially data likelihood within the cluster normalized by across all the clusters. The effective number of points are sum over the responsibility variables. It's the same as GMMs. Mean of X is also the weighted mean of X's in the cluster. The pi is also the fraction of effective data points in the cluster. So despite the underlying cluster conditional probability being different, basically the M step still look, E step and M step both look quite similar. So here's this example the book used to drive the design of this particular section, which are written digits. They carry a special place in the development of machine learning. Right? Hopefully you've heard about it in computer vision. If not, ask me afterwards. So these are 16 by 16 grayscale images consist of isolated written digits that people write on envelopes, like zip codes in America or postcodes, called here. So assume that they were segmented and sort of cropped to the same size. We now treat each of the pixels as a binary variable. We just threshold it so that each pixel is either black or white. And the top row consists of a number of these written digits. And we treat this as a, did they say 256? Well, so basically this is 16 by 16. So D equals to 256 binary Bernoulli variables. And we assume each digit is the result of like a mixture model. And we set, in this case, right. So in this case, the data point is assumed to have been generated from 3 separate components in the mixture model. And then we go ahead and run EM and try and recover what the 3 components are without knowing, assume we don't read digits. Then the underlying components that's being recovered are these. So these are the mu parameters. That's why they were not exactly black and white. They have a grayscale, right? So one of the components look like 2, the next one look like a 4, the last one look like a 3. So if we use a single multivariate Bernoulli distribution, so this is k equals 3, and if we have k equals to 1, and we do the maximum likelihood estimate, which is essentially just the mean vector will be an average of the pictures we're seeing. It looks rather confused. Somehow 3 become the dominant shape if we average over 2 and 4, but yeah, the shape is by no means clear. So this demonstrates, I guess, in like real world, but somewhat toy data sets like this, Bernoulli mixtures can be useful, and we can see it. So that's nice. All right. So we have the last part and then a bit of a modern note. Let me see. Vikram asks, is this model just for the number 2, 3, and 4? Yes, it is. Let me see. Yeah, I believe so. It might be also just for the 5 images that we see, but I'm not sure of that. I need to go check back on it, like go read this surrounding text in the book. Right, if we check in the entire MNIST and ask for 10 components, the book didn't show it, but I would guess we will get the digits back. Okay, so I still haven't convinced you that EM really maximizes the likelihood. So let's do that now. And we talked about KL divergence last week around this time. So let's use it. So as a reminder or refresher from last week, KL divergence between a distribution P and a Q is essentially the difference of cross entropy and the entropy of distribution P, right? So usually it's written like this. So it's the expectation of the log ratio of Q over P. Right, and so chiral divergence is always non-negative. And P and Q are not symmetric to each other. So one way to remember it is that like the first part, like the basis of comparison is P, and that sits in the denominator inside the log term. and expectation is also taken over that. All right, so much for KL divergence. Now, here is what the book says. It says if we have the likelihood, log likelihood of x without the latent variable, like data likelihood of the mixture models, it decomposes in as two terms. The first term is called the lower bound of the log likelihood. The reason it's called the log likelihood, lower bound, is because this KL term is greater or equal to 0, right? But you could ask, okay, what just happened? Yes, you can call it that, and you can write it as a KL. What are P's and Q's here? So there is some Q of Z. Spoiler alert. So these are related to our responsibilities. And then the P is like the lower bound has the complete data likelihood in it, and the KL term has like basically the mysterious Q of Z, actually an arbitrary Q of Z, and also the posterior probability or cluster posterior, the responsibility variables in it here. You may say you just dumped this on us. Yes, that's correct. And here's how you show it. Yeah, I remember it wasn't in the book, therefore I was writing it out. That was memory from last year. I leave you to check whether that's true. But for now, let's I'll just go through several spots in this derivation in order for us to convince ourselves, right? So we have the data likelihood equals the sum of complete data likelihood over the latent variables. That's easy. We also have Bayes' rule with logging it, which basically says, right, the log likelihood plus the log of the cluster posteriors equals the complete data likelihood. Okay, it's just Bayes' rule, nothing new. Now we just move this term to the other side, right? And we introduce Q of Z because this is a distribution over only Z. And we're talking about one data point here. Therefore, right, so sum over the values of possible values Z can take Q of Z normalizes to 1. So, okay, that's easy. So we just stick Q of Z in front of this likelihood term. That should be trivial, right? Because this data likelihood does not depend on Z, and we summed over Q of Z, so this is a constant. Now we introduce this Bayes rule term inside, use that to substitute the likelihood term. And we get essentially these two terms. One is the complete data likelihood, the other one is the posterior. And now what happens? We just introduce Q of Z again and subtract it back out. Why are we doing that? Because we know we are going towards the direction of KL divergence. And we're working with logs, and we want to make a ratio of two probabilities. So logs with opposite signs are good ways of doing it. So, okay, we just did this and we rearrange the terms. We get essentially what? The second term, right? The first term is the complete data likelihood minus log of Q of Z. The expectation is taken over Q of Z, right? The second term, we still have an expectation over Q of Z. The difference of the logs now becomes the log of the ratio of the posterior over Q of Z. And this is plugging back in the definition of KL divergence, the divergence between Q of Z and the posterior, with the Q of Z being the basis of comparison here. Hopefully you're convinced enough. If not, just know that, well, these are, this manipulation is, there is nothing really new or special in it, right? I would say, staring at the lower bound term, where it's also sort of an expectation over log ratio kind of thing, and the KL divergence term is perhaps the newest thing in here. So let's just bear with me for a bit, and let's try and understand what they are doing while we are doing the EM. Okay, so here is a graphic that we will see 3 times. This is just introducing the graphic, right? So the log of likelihood is a sum of this lower bound and the KL divergence term, right? So I think one cheeky thing that's been swept under the carpet is that this is not necessarily positive. It can be greater than 0 or lower than 0, but it does not matter because the KL is always positive, even if the log likelihood is negative. It's fine. The lower bound is still lower or smaller than the likelihood. All right, I hope this picture is okay, right? Now what happens during EM, right? And what is this mysterious Q of Z anyway? So in the E step, what we do is essentially set Q of Z equals to the posterior probability of Z. I think I've flipped the chart, but the slide haven't updated itself. Other machine. Let me see if it does. Okay, strange. Maybe my other machine is off. So maybe okay. Here it has updated. Finally, such a long lag. Right. So what we did in the E step is essentially setting Q of Z equals to the P of Z given X. And if we do that, the KL divergence term shrinks to 0. It's easy to see because KL divergence is only 0 when the 2 probabilities are equal. And what does it mean for the picture? So that means the log likelihood. For now, we haven't updated the parameters yet, so it's log of x given theta odd is now equal to the lower bound of Q of Z involving Q of Z and theta odd. That's also easy enough, right? We haven't done much work. We still haven't maximized the data likelihood. So here's picture number 3. Right, so we now maximize. So in the M step, right? So we already said we set Q of Z to the posterior. So like Q of Z is held fixed in the M step. And a few slides ago, we say that the M step, what it does is to maximize this thing. When Q of Z is fixed, so as we said, right, so there are 2 terms in this lower bound term. This thing in the bottom, basically, this is the negative. It's actually the entropy of Q of Z, entropy of Z under distribution Q. So this is fixed. We don't need to worry about it. And what we're dealing with is essentially the and summed over Z, basically taking the expectation over Z using the Q of Z or the cluster posterior, log of the complete data likelihood. So that's what the lower bound, like maximizing the lower bound, really is. And these two terms, we already saw a few times in the beginning of this lecture. They are exactly these Q terms, right? So look, this is that, and then this term is this term, right? There. And now what happens, right? So we basically changed, so the theta and inside the log is updated. And the theta outside that sits in the Q of Z is held fixed. Right, so the lower bound gets pushed up. So remember in the last page, we basically have the lower bound and the data likelihood sort of sitting together in this dashed line. And now we know by doing the M step, the lower bound gets maximized. So it gets pushed up a little bit. And furthermore, once we have a new set of theta, the KL divergence term is no longer 0, right? So we kind of also get the, like we maximize, we do this much work to push the value of the lower bound up, but we also get a bonus that the KL divergence will also be non-zero. Therefore, the whole data likelihood is also pushed up, right? So I hope that's somewhat convincing, and it's right. It's a very neat way of looking at EM as well. So we will, I guess, KL divergence shows up a lot in different types of machine learning objectives or losses, and this is one example. This is a neat way of understanding EM and also convincing ourselves that the likelihood, data likelihood, is indeed being maximized. Here's also a picture of the lower bound. And another philosophical reason we're talking about this is that in a lot of cases, the lower bound is an easier function to maximize. Therefore, it's drawn as a concave function with sort of a smooth, unique maximum here. But the original data likelihood might be this red and wiggly function. So what this picture says is if I'm sitting at theta odd and I maximize the lower bound, I get to this point theta nu, which corresponds to like a new theta, and which will have another smooth, nicely behaved lower bound function, like sitting at that point. If I further maximize that, I sort of push this up, right? So it says the lower bound is a convex function, have a unique maximum. For mixed-order components for the exponential family, you can convince yourself of that during the assignment. There's also ways, there's also a class, basically a set of algorithms that calls generalized EM that don't seek to maximize the lower bound, but we just improve the lower bound, right? Right. So in terms of EM as alternating maximization, essentially, instead of solving for the optimal theta and going there right away, we improve theta a little bit by little bit, and the other way, like as coordinate ascent, we also improve the likelihood by updating the posteriors. Okay. All right. Yeah, we can use the next 5 to 10 minutes talking about what happened since the initial development of EM and GMM in this century, or I think, yeah, in your lifetime, right? Most of you would be around or have been born since then. So this is actually a NeurIPS 2002 paper. John Kleinberg, who is a very impressive computer scientist. I often remember him for all the different contributions he made to network science. I was happy to have found that he wrote this really neat paper on the impossibility of clustering. I thought it's worth talking about it. In part because it's sort of echoing back on the perspective of clustering at the beginning of the lecture. So clustering is usually, it's sort of one technique. It's usually not the solution to your problem. And clustering has its own problems. So, and in general, impossibility results are important because it saves people the effort to find the best universal clustering algorithm because none exist. Okay, here we go. John Kleinberg's paper, here's the sketch of the main argument, right? So if he says there are 3 desired properties for a clustering algorithm. One is scale invariance. So clustering depends on the distance function, right? So for the both Gaussians and k-means is L2. You can imagine other distance functions. So that's also what's so neat about these theoretical papers in that it's actually invariant to the distance functions we use and so on. So don't try to find the best distance function, right? And any alpha greater than 0, and f is basically a clustering function, such as k-means. So for scale invariance, we desire that if the distance is simply scaled, the partition that we find on the data set is the same. The second criteria is richness, basically. Like we could find all possible partitions of a data set. And the third one is consistency. Basically, if there is a tricky term here where it's called gamma transformation, it basically says what gamma transformation means is it like shrinks distances between points in the same cluster. And then expands distances for points that are not in the same cluster. So basically, if we have 2 distance functions and also a partition function of the former, where the second distance respects the the clustering in the sense that it shrinks points in the same cluster, but expands it for points that are not in the same cluster, then on the new distance metric, we should get the same clustering. Turns out John Kleinberg primarily analyzed what's called single linkage clustering algorithms. If you've taken data mining or something similar, you will know that we start with every point in its own cluster, and then we start merging clusters one at a time, right? So there are, for example, different ways of performing single linkage cluster. You can stop when you have k clusters. You can stop when you have, like when you try to connect clusters distance more than r apart, and you can also limit the length of the links you make with respect to either the maximum distance in the data set or average or something. It's called scale alpha. Turns out none of these satisfy all 3 properties, right? So the theorem in the book actually says there is no cluster function f that satisfies all 3 simply like innocent properties. Neither do k-means actually. So k-means in the paper is presented as a special case of a centroid clustering algorithm, and it does not satisfy consistency. Oh, oops, bad news. So the same thing goes with like the very contemporary machine learning topic of fairness. There's about garden variety of more than 20 fairness metrics, and there is no one fairness classification algorithm that satisfies all of them, and it has been shown that they are actually contradicting to each other. Anyway, so that's a sidetrack. Let's talk about k-means plus plus. Which is another really neat theoretical paper published in 2006. I'm still waiting for the page flip. I don't know if you can see. Anyway, I'll just stop talking. Hopefully on my screen it will refresh. Yes, there we go. It's a 2006 SODA paper. So SODA is the primary, one of the primary computer science theory conferences. It's done by Sergey Vasilevsky and David Asser. I couldn't find David Asser on the web, but Sergey is still very much active in machine learning, at the intersection of machine learning and algorithm, which is very cool. If you can go scan his latest papers. So this paper, it basically says k-means, it does find a local optimum, local minimum of squared distance from the centroid, but it could be arbitrarily worse than the global optimum. Oops, bad news. Same thing can be said about Gaussian mixture model as well, because yeah, there are many, there's identifiability problem with different mixture components, which I believe we'll touch upon when we talk about neural networks, but it's also just a local optimum, right? Sergey and David basically says, hey, there's a fix. We want to attack this problem by actually attacking the initialization component. The algorithm summary, well, this is on Wikipedia already because it's k-means plus is so widely used these days. So we first choose one cluster center uniformly if we want to end up with k cluster centers and a data set. And then for each data point that are not yet chosen, we compute its distance to the nearest center that's already been chosen. And then we sample, essentially, a new data point at random using a probability proportional to the minimum distance to existing centers. It doesn't have to be dx squared. In Sergey's paper, he did a more general case of dx raised to the power of alpha, but square distance sounds good. And then you repeat this until k centers have been chosen. After that, just run your k-means update. It's still good. The neat thing is that he's shown that this k-means plus plus is roughly order of log k approximate, meaning that the distance we get is, if there are, let's say, 8 centers, then log of 8 is maybe, worst case, 3 times worse, but not a lot more worse. So which is encouraging. So this is now widely used, right? What do you do in practice when you do actually k-means or Gaussian mixtures or other mixtures? You normalize your data. You use k-means plus plus to initialize k-means, right? sklearn does it for you. And then you use k-means and spherical covariances to initialize a Gaussian mixture model. You can try a number of different initializations, basically run your k-mean a number of times. Also, if you invoke sklearn, it will by default run your k-means 10 times before it gives you a result. That is to try multiple times so that we make sure we're not stuck in the worst local minimum, local. So that's that. That's all for today. We covered what is the M-step maximizing, what is EM maximizing, is EM really maximizing the likelihood, we use KL divergence for that, and then we looked at what can clustering not do in k-means plus plus. Let me check questions. No questions. that's pretty good. Just going to pause here. Feel free to let me know if you want me to go back to something as well. Try and see if I can pull up the questions on my phone so that I can look at it. If not, I hope people are all happy with additional like the new perspective of EM, and I believe this will give you enough to attempt everything in the assignment 1, which is also good news. Otherwise, I will see you after Canberra Day, hopefully in person. I need to check out the room and stay tuned on the COVID situation. And also quiz, there's a quiz due next week, so expect it to be released in the next few days. But we'll watch out on Piazza for that. Is that I'm going to try and tell Teams to stop the recording.